very easy to understand. So if you have any genealogical details, or how people have referred other textbooks or research papers to write their papers, no, if you want to link that, or if any generation details, okay, this person is a parent and his children are this one, his children are this one, like that. If you want to give the details, we can represent through the trees. Okay, so here if you see, one simple example is, so you can consider like how the things are derived from one another. For example, you can assume that like Jawaharlal Nehru was there, then after that Indira Gandhi. Okay, so after Indira Gandhi, like overall the Rajiv Gandhi was there, Sanjay Gandhi. Okay, so like that, if you want to put it in a tree format, you can put it. Okay, so the generation details. Okay, and that's why we use trees. Okay, in trees we'll be having more number of one or more number of nodes will be there. Parent node will be there, and we will have the children node. Children nodes will be having for them. Okay, not mandatory that all the nodes should have the children node, nothing mandatory there like that. Okay, and one node will be the root node, and you will be having many subtrees, like subtree 1, subtree 2, like that you will be having. Okay, and for the trees we can find out what are the levels and depth. Okay, so for example, if you see the root node is in level 1, the root nodes, children nodes are B, C, D. Root node is A. Children nodes are B, C, D. They are in level 2. And B node has E and F as children. C node has G as the child node. And D node has H, I, J as the children nodes. Okay, so here the nodes E, F, G, H, I, J means the children nodes of B, C and D are in level 3, and the next level nodes are in level 4. They are the children of node E and H. They are there in level 4. Okay, so what is the height of tree? How many levels are there in the level in the tree? How many levels are there in the tree? If you measure it out, you will find out the height. Okay, and for each and every node we can find out how many nodes are connected to it, how many edges are connected to it. Based on that degree of the node we can find out. So similarly we can find out in degree and out degree also. Okay, how many incoming nodes are there and how many outgoing nodes are there. Okay, so based on that, in degree and out degree also we can find out. Okay, so here if you see, so what is the degree of the node? How many subtrees are connected to it? So based on the degree we can count. 1 second, I'll just drink water. Okay, so if a node, if it is a leaf node, okay, so how to determine it? It will not have any children node. Okay, then that node will be terminal node. Okay, and if a node is having subtrees, then that will be called as parent node. Okay, from the subtrees only the children nodes will be identified. And in the same level, if there are nodes in a tree, they will be called as sibling to one another. Okay, and through the edges from the children node to parent and from the parent to its parent. Like that, if you go, you can find out the ancestors. So now we will see the representation of trees. Okay, so here if you see, A is the parent node, its children node are B, C and D, and B has a children node E and F. E has a children node K and L. C has a children node G. D has a children node, child node H, I, J, and H node has a child node M. Okay, using the bracket we can represent through the list representation. Okay, so the same thing if you want to put it in the linked list. Okay, so the data node will be there. What are its children node? For them we have to create link and we have to represent. Then the next one is left child, right sibling. Okay, so here if you see, the data is A. Okay, for the first node the data is A, and the leftmost child is B. A is not having any right sibling. Okay, now if you see for B will be there here in the data field. Its leftmost child is E. What is the right sibling of it? F. Okay, so here if you see for B also, here the left child is E, the right sibling is C. Similarly for E, if you see, the data is E, left child is K, the right sibling is F. Okay, so like that it will be stored in the left child right sibling notation. Next is binary tree. So binary tree, it's a group of nodes. Okay, so even if you have empty tree, no nodes are there, that also binary tree. And in binary tree you will be having left subtree and the right subtree. Okay, and not mandatory that all the time you should have both the subtrees. Either one of them may be there or none of them will be there, or both of them may be there. Okay, and if you have this left child right sibling representation of the tree, we can convert that to binary tree. So left child right child tree representation of tree. Okay, so this is what we have discussed here already. Okay, the same thing it's shown here. Okay, so now that tree, from if you have this this left child right sibling tree, we can form the binary tree. Okay. So now let us see the abstract data type of binary tree. Okay, binary tree shortly will be called as bin tree. Okay, so it is having finite set of nodes. It may be empty, and each and every node can have left subtree and right subtree. Okay, so those values may be null, or the trees may exist. Okay, because the left subtree, left child and right child may exist or may not exist. Okay, so accordingly the values will be stored. Okay, so now initially we have to create the binary tree. Then after that what we have to do, if you want to check whether the tree is empty or not, then you can check that if binary tree, if it is empty, then it means that okay, so if you want to check whether the binary tree is existing or not, then what you can do, you can give is empty of binary tree, the root node value you can pass. It will return, if the tree is existing, it will return false, because we are checking is empty, is the binary tree empty or not, we are checking. Okay, so next one is make binary tree. Okay, it means that we want to put the values into the binary tree. That time you have to pass what is the data you want to put, what is the item you want to put there, whether you want to put it as right binary, you want to insert the item in the right or left, that value information also you need to pass. And if you want to find out what is the left child of a particular node, okay, so first you'll be passing the node address. If the node address, if it is empty, then it means that that node is not existing. Otherwise, of that node, whatever we have passed, for that node, left child we want to find out. Okay. And here, if you want to find out in a node what data is there, if the data, whatever the data in a particular node, if you want to retrieve, what we can do, if is empty of binary tree. So we want to check whether the node data, whatever you want to access, if the data is existing, means we will. Okay, so if the node is existing, then we will we'll fetch the data from the node and we will display it. Otherwise, we'll tell that that node is not existing. Okay, then if you want to print the right child of a node, for that what we have to do, first that node is existing or not, we have to check using isEmpty function. If it is not, if it is empty, then it means that that node is not there. If the node is not there, then right child also will not be there. Okay. So if the node is existing, then only what is the right child of it we will fetch and we will return it. Okay, so now let's discuss about the some of the different tree types. Okay, so the complete binary tree means you can see here only in one level, no, the difference can be there. Okay, so here if you see all the nodes are A node, B, C. All of them are like completely filled, but in the D node H and I are there, but E, F, G they are not having the children nodes. Okay, so in the in one level, the last level, in the final level, the node can be like they can have the children node or not. In that level it can be differing. Okay, and the next one is skewed binary tree. If you see here the first one, if you see first binary tree, if you see A has the child node B, B has child node C has child node D, and E, like that it's going. Okay, only one side, no, left side the children nodes are connected. So that is example for a skewed binary tree. It's like only one side, it is too many children nodes are connected. Okay, so now let's see some of the properties of binary tree. Okay, so the maximum number of nodes in a level I in a binary tree, the formula is 2 power I minus 1. So how to find out maximum number of nodes in a particular level I in the binary tree? Formula is 2 power I minus 1. So I value should be greater than or equal to 1. Okay, and if you know the levels, total number of levels, okay, the depth or height of the tree, if you know. Okay, if the height is k, then how many maximum number of nodes in that binary tree? 2 power k whole thing minus 1. Okay, so that is a formula. So what is the relationship between the number of terminal nodes and the nodes, how many nodes are having degree 2? Okay, so in a binary tree, if it's not empty, then okay, n naught is a number of leaf nodes. Okay, n naught means they are not having the children nodes. The nodes which are not having children nodes, that is n naught. And n2, the nodes which are having the children nodes as 2. Okay, so n naught equal to n2 plus 1. Okay. So what is full binary tree and what is complete binary tree? Okay, they are totally different. Okay, so the full binary tree of depth k or height k, okay, or the levels, okay, total number of maximum levels in a binary tree, okay, depth k having 2 minus 1 per k nodes, k greater than or equal to, okay, here if you see here in this example, Okay, in all the levels, no, the nodes, all the leaf level, terminal nodes will be in the same level. And all the other parent nodes, if you see, all of them will be having 2 children nodes. That is full binary tree. Okay, and complete binary tree means a binary tree with the n nodes and depth k. Okay, that we'll call it as complete binary tree. Okay, so correspond to the nodes numbered from 1 to n in the full binary tree of depth k. So only in one level, okay, in the here the terminal nodes are then hi here for the node d, and for the other nodes it's efg. Okay, only in one level the difference is allowed if you want to construct the complete binary tree. So the next one is binary tree representation. Okay, so if you have a complete binary tree, okay, if n nodes are there, okay, so if you want to store the parent, if the parent of a node, okay, if it is stored in the location in the array, then left child of it will be in 2 into ith location, and right child of it will be there in 2i plus 1. What? Ina? Po. Okay, so this is very important. We may you may get some question from this. Okay, sometimes easy questions you'll get. If the parent is in ith location, okay, then left child will be in 2 into I location, and the right child will be in 2i plus 1 location. Okay. Okay, and similarly, if you get a child node, okay, if the left child is in 2i, how to find out where it's parent? Okay, so I by 2 you have to do. Okay, so now this is a sequential representation using array, how to store the binary tree in the array. Okay, so here the first diagram it's showing the skewed left side skewed tree. Okay, so A is the parent, it's in location 1, B is a child, so 2i, okay, B will be stored, okay, and B is in location 2, so 2 into 2, in the fourth location C will be stored, like that. Okay, so into if the parent is in ith location, left child will be in 2i, and right child will be in 2i plus 1. So here also you can see that the parent A is in one location, 2i, in 2i location B will be stored in 2i plus 1 location, 2 into 1 plus 1. In the third location C will be stored, and so on. Okay. The same way here B is in location 2, and in the fifth location D will be there, and in the sixth location 2i plus 1 location E will be there, and so on. Okay. Okay, now let's see the linked representation. Okay, so so here if you take each and every node, we have the data field and the left child link field and right child link field. Okay, so node you have to create within it what are the fields we need, data field and the tree pointer for left child and the right child. Okay. And what are the different binary tree traversals we can perform? Okay, so we'll be having the node and the left child and the right child. Okay, so we may have different types of tree traversals. The first one is Inorder Traversal, the second one is post-order traversal, and the third one is pre-order traversal. Okay, so here in Inorder Traversal, what will we do? We'll visit the left child, then the node, the parent node and the right child. That will be Inorder Traversal. If it is post-order traversal, we'll visit the left child first, then right child, then the parent node. If it is pre-order, first we'll visit the parent node, then the left child, then the right child. Okay, this will be like iteratively this will be happening. Okay, so the next one is arithmetic expression using binary tree. So if you have the Inorder Traversal, okay, if you want to perform here, okay, this is the arithmetic expression. It is stored in the binary tree here, okay. So here plus is the root node, star E or children of it, star has star and D as children node, star has slash C as the children node, and slash has A and B as the children nodes, okay. To represent the terminal nodes, to terminate them, this blue color boxes, no, they are like representing their terminator, okay. So now in the Inorder Traversal, how will we do? A slash B, then star C, then star D, then plus C, okay. So that is Inorder Traversal. If it is pre-order traversal, how will we do? Plus, okay, then star, then slash A, B, then C, then D, then E. If it is post-order traversal, then A, B, slash C, star, D, star, E, plus. Okay, if it is level order traversal, then plus, star, E, then star, D, then slash C, then A, B. Okay, so level by level we'll finish it off. Okay, so now how will we write the code for Inorder Traversal? For Inorder Traversal, we'll pass the root node address first. Okay, so this is a recursive version. So if the node is existing, then in order left child, the left subtree we have to traverse. Okay, then come to the parent node and print the data in it. Then the right child, the right subtree in order manner recursively you have to call. Okay. If it is pre-order traversal, what will we do? We'll pass the root node address first. Okay. Then if the pointer is existing, okay, in pre-order first the parent node data will be, visit. Then after that in the pre-order, in the recursive manner, the left child, the left subtree will traverse. Then after that in the pre-order manner, the right subtree will traverse. If it is post-order traversal, what will we do? Will be passing the root node address here. This is again a recursive call. Okay. So if the node is existing, then in the post order the left subtree will traverse. In the post order the right subtree will traverse. Then after that parent node data will be visited. So this will happen in recursive manner. Okay, in the apart from recursive manner, in the iterative manner, if you want to do, how can we do that? Okay, so that we will see. So in the iterative in order manner, also the root node data will be passing. Okay, and in here we will be making use of stack pointer. Okay, so we will here the top pointer will be equal to -1. Okay, initially we'll use a stack here. Okay, so till we traverse all the nodes, it will be in a loop. Okay, so here every time we will fetch the left child and we will do it. Okay, and whenever you are visiting a node, that node will be put up into the stack. Okay, and if it is after adding that into the, so like that again and again till all the left children will be fetched and they'll be added onto the stack. Okay, then what we will do, we will start removing them one by one from that, and we will visit the data in it, and then we will be visiting the right child of it. Okay. Okay, so here how will we trace the operations of Inorder Traversal? Okay, so here this is the tree we have taken. Okay, so if you want you can take a snapshot of that. That's what we will refer there. Okay, so A slash B star C star D plus E. Okay, so one by one they'll be traversed here. First the plus node will be visited. Okay, and the children node of them. okay, will be visited one by one. Okay, once if they are in the Inorder Traversal, if you see, first the parent node will be visited, okay, then after that the left child of it will be visited, then the right child of it will be visited, then after that, like that will be in the recursive manner, again and again it will be carried out. Okay, whenever we are visiting the parent node, we have to print what is the data in it. Okay, so that is in the expression tree only when we visit the operands, we'll be printing the value of it. Okay, other times we'll not print it. Okay, in the level order traversal, what happens, we'll make use of the queue. Okay, so even if you want to see like how it is happening, like even using the scribe pad I have explained during the regular semester, you can see that here only in the PPT I am explaining. Okay, you can refer the scribe pad like with example in queue how will it be stored and all, we have explained regular semester. Those links if you have, you can please refer to that. Okay, so it is there in the repository. Okay, so here in the level order thing, what happens, for example, A is the parent node, then if you have B and C, what happens, first A will be visited. Okay, so we will make use of queue for level order traversal. Okay, initially front and rear will be 0. So if the root node passed, if it is null, then we are returning it. Otherwise what we are doing, we consider A, we have only 3 nodes. A is a parent node, B and C are children nodes. Okay, so A will be pushed on to the queue. Okay, so now till you reach the till infinitively, here we will do, but once if the queue become empty, we will terminate the loop. Okay, that's the way how we'll terminate. It looks like infinite loop here, but where we put the exiting point, when the queue become empty, we will come out of the loop. Okay, so here we are removing A from the queue. Okay, for the example what I have taken, only 3 nodes. Okay, A is a parent node, B and C are the children nodes. Okay, so A is existing, so A data we will print it. Then after that the left child of it we will retry. Okay, so here in this is level order traversal. So for that the left child of it we will fetch and we will add that onto the queue, because the left child also will have the subtrees, right? The children it may have. In this example A, B, C, only 3 nodes are there. Okay, so after visiting them we are null will be inserted when you have only 3 nodes where B and C are the terminal nodes. Okay, then the right child of A node is C. Okay, that also will be pushed onto the queue. Okay, so now if you see here, we'll try to remove the content from the queue, but null value we have inserted because B is not having any children node. Okay, so if pointer will be null, so we'll come out of the loop. Okay, so here what happened, we these statements, all these statements are within if condition, so they will not be executed. So we'll go to the next point, and one more entry will be there. Okay, the children nodes of C also not having any children node. When we remove, null will get, so it will come out. Okay, so here at any point of time, if you have null values, it will come out. So in that way the level order traversal will work. And the next one is copying binary tree. Okay, so how can you copy one binary tree to another binary tree? Okay, so here you can consider tree 1 you want to copy to tree 2. Okay, so original tree we want to copy to another tree. So here we are creating another temporary node. So if the original tree is existing, then what we do, we create a link list node. Okay, empty node will create. Okay, if there is no memory space, we'll tell the user that memory is full. Else what we'll do, we'll copy the left child of the original tree to the new tree. Okay, we want to create the copy of it. Then the original tree's right child we will copy to the right child, and data also will copy. Then finally we will return where we have copied. Okay, so now you want to check whether two trees are equal or not. So that how can we do? Okay, so here equal of we want to check whether the tree 1 is equal to tree 2. Okay, so tree 1 and tree 2 both should exist. Okay, then after that here if both of them are existing, then if their data are equal and the first tree's left child and second tree's left child also equal, and the first tree's right child and second tree's right child also equal, then we will return that both the trees are equal. This will be repetitively happening for all the nodes. Okay, so next we'll go on to the next topic, which is very easy, propositional calculus expression. So arithmetic expression, how can it be stored, I told you. So now we are going to see the propositional calculus expression. Okay, so only if you have a variable, that is an expression, and if you have negation of x, x intersection y, x union y, all these are some of the expression. Okay, and if you have the expression x1 or x2 and negation of x3. Okay, this is one of the example for propositional calculus expression. Okay, so now let's see what is the satisfiability problem here. Okay, with respect to this. So by substituting different combinations of values for x1, x2, x3, okay, if the propositional calculus expression generates 1, okay, then those values will be the satisfiable values. Okay, so we have three values, x1, x2, x3. So true, 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 false, true, false, true, like that, different combination. 3 means 2 power 3 values. Okay, 8 values, 8 combinations of values will get. So substitute them. Okay, so for which value it generates true. Once if we find out, that is a satisfiability value. So here, similar to the arithmetic expression, here what we do, we will put the operators and the negation and all and or values will be in the interior nodes. The operands will be in the terminal nodes. Okay. So here, if you see the node structure, it will be like left child, right child, and the data will be there and the value. Okay. So here the operators, logical operators are not and or, and here the logical values are true and false. Okay, and within the node, if you see, we will be having the left child, right child, and the data and the intermediate resultant value. Logical data means what is the operator, and value means 0 or 1, that value. Okay, so all the 2 power n possible combination for so many times, okay, we'll have to generate the true false values and substitute for those variables, and we have to evaluate them in the post order evaluation, which you have learned as the stack application. Okay, so for which one it's returning 1, for which are all the values it's returning 1, we have to see. Okay, if it's returning 1 for any combination of value, then we will tell that yes, satisfiable combinations are there. If none of them it's generating, then it means that no satisfiable combination. Okay, so for the post order evaluation, how will we write the function here? Okay, if the node is existing, then what will we do? Post order evaluation of the left child, then post order evaluation of the right child, we have to call it. Then after that, for the parent node, we are going to check. If it is not, okay, if the operator is not, then what we have to do? We will have the variable value in the right child. Okay, it is a it's a only one operator will be having. It's not a binary operator. Okay, not a unary operator. Okay, so the right child value negation, if you find out, you will get the value of it. Okay, and for and, what will you get? The right child value and left child value. If you find out the node value, parent node value, you will get. Or means right child value, or with the left child value, you will get the parent node value. Okay, and here if you have true, then we have to return true. If you have the false operand, then we have to return false. These are all enumerated data. Okay, so now let's move on to the threaded binary tree. Okay, so here uh, we will be having in the binary trees, if you see the parent nodes and children nodes will be there. Some of the nodes will not have the children nodes. Okay, so if you want to mention that they are not having the children nodes, the thread we can create. Okay, so those threads, will call them the null pointers. No, they will not have the children nodes, right? So those values, those links, we want to point to the point to the parent, or who is the successor of the node, who is the predecessor of the node, that and all we want to point. Okay, in that way we can create it. Okay, so if in the threaded binary tree, if the left child is null, then what will we do? The left link of the pointer will point to the predecessor of it, okay, in Inorder Traversal. And if the right child is not there for a node, then the right child link will be pointing to the next node, successor of the node, which will be visited in Inorder Traversal. So this is a example for threaded binary tree. So we have A, B, C, D, E, F, G and H, I. Okay, what is the Inorder Traversal of it? H. We have H, D, I, B, E, A, F, C, G. That is the Inorder Traversal of it. So here if you see in a binary tree construction, the H will be hanging. Okay, so for that what we can do, this dangling values, we can make them to point to the root node. Okay, and here if you see, so here if you see H, I, E, F, G, they are not having the nodes. So how can we efficiently use them? So we can make them to point to the successor. So H's successor is D in Inorder Traversal. So it's not having right child, but the right child link we can make it to point to D. Okay. So similarly, I is there. Okay, I also not having the left child and the right child. Okay, so the left child link you can make it to point to the predecessor, which will be visited in Inorder Traversal. The predecessor is D in Inorder Traversal, and the successor for I in the Inorder Traversal is B. So those links accordingly we have to make them to point to. So if the children nodes left child and left child, if it is not there, the left thread will become true. If right child is not there, the right child will become true for the particular node. Okay. So whenever the children nodes are not there, then what will we do? We'll use a thread to point to the predecessor or the successor. So that time the thread will be true. If the child is existing, then that time the thread will be false. Okay. So here if you see in the structure construction for the threaded tree node, we will have the left thread, right thread, and left child value, right child pointer value, and what is the data in the node. Memory representation. So here memory representation of a threaded binary tree. See here we are using a header node also. Okay, so the header node will point to the root node. Okay, root node children nodes are existing, so the thread will be false. Root node has the children nodes B and C. and B also has the left child and right child, so the threads will be false. For example, if you see for any particular node, if you see here, B's right child is E, it's not having any left child or right child, so the thread will be true. Okay, it means that the E is not having left child. E is right thread also true. It means that right thread is going to point to the successor of the node E, which will be visited in Inorder Traversal. Okay, so in that way, the threaded binary tree you have to construct. So how to construct? If you give a binary tree, you should know how to construct threaded binary tree. So such questions also we have asked previously. Okay, so now let's see how to find out the inorder successor of a node in a threaded binary tree. Okay, so here if you see there are nodes, and here the triangular shape shows it's a subtree. Okay, and here the tree we will be passing a particular node address here, and inorder successor of it we want to find out. Okay, so in Inorder Traversal, how to find out the successor of it? We have to visit the, here if you see what is the inorder using Inorder Traversal, what is the successor for B? Successor of B is its right child. Okay. Similarly, what is the successor of A in this example for the Inorder Traversal? It is C. And the same way for other things. Okay. So that's why the right child we will be checking. If the right thread is not there. Okay. If the right thread is not there, then what we have to do till we reach the null values for the left thread, till it becomes not true, till that time we have to fetch, and we should find out the left child of it. Okay, so in that way the inorder successor we can find out. Then for Inorder Traversal for threaded binary tree. Okay, so here for Inorder Traversal we are going to repeat the loop till we reach the null values. Okay, so here the inorder successor function also we will call till the temporary node is existing. You are going to repeat this loop, and whatever the data in it will print it. Okay. So next is inserting a node into a threaded binary tree. This is also very interesting one. Okay. So here if you see we have example binary tree A, B, C. Okay, so we want to insert D as the right child of B. Okay, so what are the changes we will be doing? Okay, we want to make D as the right child of B. So now B is previously it's having a thread. Okay, so now B we have to make it to point to this thread we have to break, and the right child we have to make it to point to D. Okay, and where B was previously pointing, it was pointing to the header node. So that value we have to copy to D. Okay, and now D is a child node. So its left link we have to make it to point to B. D is not having either left child or right child. So the left thread and right thread will be null. Okay, so in this way. So in this way, we will be handling the threaded binary tree insertion. So similarly, if you are inserting a new node as a left or right child for C also, you should know what are the changes happening. So with that, I will wind up today's class.